Good afternoon, and thank you for joining. The wind power is increasingly seen as a key technology enabling the transition towards sustainable clean energy. In the US, wind power currently accounts for 8% of domestic energy production, but this share could grow significantly upwards of 35% or higher by 2050. So, with that context in mind, it's critical to have national perspectives of wind power and the role that it might play in advancing ambitious clean energy goals, to be able to inform investment strategies and also understand the collective impacts of various deployment strategies. The challenge with understanding wind power potential is that it's highly geographic in nature, and depends on localized factors and is subject to interactions with wind power technology that continues to evolve. So we need methods that can illuminate understanding for how technology innovations can help advance these ambitious wind power goals. To investigate these pathways, we need models that can capably evaluate and explore design space, to identify emerging opportunities and better characterize trade-offs and the implications of this growing source of energy. One of the challenges is that there's a persistent trade-off in the wind energy modeling community between model fidelity and scalability. So models that have higher fidelity that can better capture the physical processes that are relevant that determine how much power any arbitrary wind plant configuration can extract from the wind tend to be computationally very expensive, given sort of the physical representations that they encode. And so these models are often designed to answer narrowly defined research questions for limited sets of conditions, or technologies or locations. And increasing what's needed is methods that can not only sweep evaluations of design space, but also geographic space to understand what does the landscape of opportunity look like. And we think that surrogate model applications as driven by AI offer a path forward where we can maintain this level of fidelity, but also improve the flexibility to improve our understanding of broader conditions that might enable different technologies. So conventionally, how this works is that full form models here, we call those wake models for evaluating wind plant performance, are used to predict outcomes that we care about. And so for a wind plant, that's often how much energy could this wind plant produce over a given year. The challenge, as I alluded to earlier, is that the physical representations can be quite computationally expensive and burdensome. And so these models that are typically designed for limited sets of questions can't simply be applied at many locations across the country, and to evaluate various design scenarios. So we need different methods for answering those types of questions. So what we propose in this talk is to develop a surrogate model that can learn an efficient mapping between input data and the outcomes, as are driven by the relevant processes. So the surrogate model, in this case, is built off of Flores, which is an open source model for evaluating wake interactions and wind plant output developed by the National Renewable Energy Laboratory. And that tells us about plant level performance that we care about. And so in this talk, we'll talk about a graph neural network that we propose to learn this efficient mapping that can help overcome these challenges with the scalability while maintaining those insights that we care about from the higher fidelity model. To do this, we represent the wind plant using a graph neural network structure. So the wind plant itself is the graph. The turbines are represented as nodes, and interactions between turbines, which construct wake effects, are encoded as edges within this graph neural network structure. The graph neural network model is composed of a series of GraphNet blocks that propagate information through the graph using a combination of update and aggregate functions. We chose the graph neural network structure because it's highly flexible, and we hypothesized that it would translate well to the types of problems that are encountered in wind plant modeling. So recognizing that the model is only as good as the data it's trained on, we invested significantly upfront in developing an extensive database of simulations that the model could learn from. In total, we conducted over 250,000 simulations using the Flores model, which is a significant sample size that was designed to cover variations in plant performance that are driven by key design and operational parameters. So we looked at a wide variety of wind plants ranging from 25 turbines upwards of 200 turbines, and also looked at diverse atmospheric conditions and control strategies that are implemented at the turbine level. One of the challenges we face is that there are limited numbers of real-world samples of wind plants in the U.S., and so we needed to develop methods where we could automate or augment the construction of relevant wind plant layouts. So we generated synthetic training data to augment the information that our model could learn from. Importantly, we withheld 5% of the simulations to be able to evaluate how well our model generalizes to conditions that it hasn't been trained explicitly on. So against this 5% test data, the model generalizes exceptionally well against all the measures that we might typically care about, including root mean squared error, mean absolute error, and R squared. So the model gives us three types of outputs. On the bottom left, there's plant power. In the middle, it's turbine level power output. And on the right, it's turbine wind speed. And across all three of these outputs that our network gives us, we see that there's exceptional correspondence between the predictions that our wind plant graph neural network model is giving us in the ground truth as indicated by the Flores model. So now we shift our attention to an example illustration of how the model performs in near real time. Here we're showing an example wind plant layout in the upper left where each dot is a turbine. And what we do is we rotate the inflow direction to see how the plant performs as the wind shifts directions. So the bottom left graph, the bottom graph tracks the total plant level power output as a function of this rotation angle. Importantly, the model captures characteristic behaviors that we'd like to see, including that there are two angles of inflow direction where there are maximal waking interactions between turbines, where the plant level power output drops. And we see that the model is able to capture that with really high fidelity and accuracy. In addition, our model can not only predict power output for a specific inflow condition, it can be used to evaluate a response surface, as shown here in the upper right, which is a reflection of how much power is expected for this arbitrary plant layout under a comprehensive set of inflow conditions. This is important because if we can do this, we can combine these predictions with information on site level wind regimes to estimate how much energy could be produced by the plant across all inflow conditions. So one of the motivations for developing surrogate models is to be able to understand how technology innovations can change the landscape of opportunity for wind power. One of the key innovations that's on the horizon is known as wake steering. So in the image on the lower right, we have an animation showing what wake steering is. It's the intentional misalignment of the turbine rotor with incoming wind in order to reduce waking effects to downwind turbines. This can be significant under particular atmospheric conditions. Waking effects can be detrimental and can reduce the total amount of power that a wind plant can produce. And so wake steering is an exercise that enables developers potentially to maximize the power output that a plant can have. There are some other benefits as well. It's been theorized that implementation of wake steering could potentially enable greater siting flexibility by allowing for a more dense packing of turbines on the landscape without hurting energy production. So there's some important implications of this technology innovation. One of the challenges that methods for doing the optimizations to determine what the appropriate yaw angles for wake steering are quite expensive. And so we need other methods to be able to do these types of evaluations. at the national scale. So what this looks like using our trained graph neural network model, here's an example in the upper right where we've got a simple case of 5 turbines in this hypothetical wind farm. On the right, you can see the inflow comes from the right and moves to the left. And over time, the graph neural network is able to accurately predict the optimal yaw optimization to maximize plant level power, even if it means sacrificing the power output for an individual turbine. So this is an important outcome that our model is able to reproduce. So we've used automatic differentiation of our model. This enables a really kind of rapid estimation of these optimization routines. And we can scale this type of assessment nationally, which is one of the critical aspects of this approach. It becomes even more critical when we think about the scale and magnitude of wind power and the future role that it's projected to play. So here I'm showing an animation for a recently published scenario that examines the role of wind power in achieving 95% carbon reductions by 2050. So these are ambitious goals, but they're increasingly being considered. And what we see here is that the projected build out of wind power across the country is significant. So by 2050, in this scenario, it's projected to have an additional 700 gigawatts of wind power. And wind power is projected to take place in many regions across the country. And so there's significant sustainability implications of that. And there are also interactions with technology. And so we want to know, given this scale of transition that we're talking about, what potential role could technology innovation play? So one of the challenges, those questions we're interested in answering is how do you minimize the footprint of wind power while it's expanding at this scale? There are a number of sustainability implications around the geographic footprint of wind power related to social, economic, and environmental endpoints. And so there are reasons why you'd want to minimize this footprint even while expanding deployment levels. So we can use our network to really efficiently answer this question in ways that would not be tractable using conventional methods. So we present here a demonstration of spatial optimization using this wake steering technology. So in the lower right, we can see that using wake steering, we're able to pack turbines in closer and closer together to minimize this geographic footprint of this hypothetical wind plant while maintaining comparable levels of annual energy production. And so our surrogate method gives us an approach that allows us to do this type of exercise for all 7,000 of those build-out locations across the country. This would not be feasible using conventional means. And so one of the really exciting things is that these methods give us an ability to generate a collective understanding for what are the aggregate and cumulative impacts of technology innovations at the national scale, given the magnitude of deployment that's increasingly being discussed. So our AI surrogate models offer new insights. One of them is that wind power's footprint can shrink under implementation of this wake steering technology. So in this demonstration, again, for 2050, we show that using this technology, we could potentially reduce the cumulative footprint of wind power by approximately 10,000 square kilometers, or 14% of what it might be otherwise. And so this is impressive. And in some cases, the footprint reductions are even higher. In addition, what this tells us is that wake steering can increase energy yields per unit area. So this could create new opportunities for wind power deployment in regions that are conventionally land constrained. And so these methods, again, help us inform this big picture. So in conclusion, our network enables streamlined optimizations and exploration of parameter space. It catalyzes understanding of collective impacts of technology innovations across wind plant design scenarios. And AI surrogate approaches can leverage critical aspects of higher fidelity models without sacrificing scalability. This is one of the most critical pieces and supports big picture assessments of renewable energy that are increasingly needed. Thank you.
Thank you very much, Dylan. Very interesting talk, and the graph about the goodness of fit of your model were really impressive. So let's get on with it with questions. There is none at the moment in the chat, but I'm pretty sure they will appear. So I will make one myself. And the question is, the first question is the typical one from a computer scientist, that is, are the models open sourced? Can we find something over the internet, and can you give us some pointers to these researches?
Yes, so the plan is to release these to make them open source. That's probably I don't know, a month or so out at this point, okay. But they will absolutely released, because that's the goal, is that we want to make these kinds of analyses tractable and accessible for a broader research community. And at the national lab, we have access to a supercomputer, right, which was necessary to train the models. The key with the surrogate models is once they're trained, they're very light and efficient. And so, if we can take on that initial investment and burden, we think we could be doing a valuable service to the community by releasing them. Yeah,
that could be very, very useful, and maybe having also something which works as a service, like some kind of API people can connect to, maybe for a research project or even for industrial project. That would be very, very interesting and useful for the community. Another question, maybe a little bit more practical. It may be hard for an amateur like me, for example, or many people, I think, in the audience which are not very familiar with the world of wind farms, to appreciate how impactful and how important is this kind of optimization. Can you give us some intuition about the difference of an optimized layout of a wind farm and not optimized one? How much difference can it make to carefully design how to place wind turbines in terms of, let's say, land area used at the same capacity of the wind farm, or the other way around, or maybe in terms of cost, in terms of dollars?
Yeah, it's a great question. It's optimization in the field of wind engineering is a really big question that's been studied intensively over decades. What we're able to show here, which I think is maybe newer, is just the scalability of doing these types of exercises, and to understand maybe what is the distribution of those effects and impacts when done at the national scale, as opposed to just focusing at the site level. But to give you some intuition for how much of a difference these optimizations can make, I think that graph I showed, for the cases that we looked at, there were some instances where optimization could reduce the footprint upwards of 30%, which is significant because land has costs and other uses and their environmental and social considerations, and so that can really matter. And then in terms of energy production, it's sensitive depending on the wind direction, but under certain inflow conditions where the wind is sort of maximally aligned with turbines, that could cost the wind plant upwards of 30-40%. So aggregated across the year, those impacts may not be as bad in terms of net energy losses, but optimization can really matter depending on how frequent certain atmospheric conditions are.
Great. Thank you very much for this clear and elementary explanation. We have questions from the audience, so I think there is still a couple of minutes to answer them. So, does wake steering involve extra stress on the wind turbines? If so, could we optimize both power outcome and wind turbines durability? That's a good one.
That is a good question. There are certainly trade-offs with, I'd say, imposing any type of controls. In general, I think one of the benefits of wake steering that's hypothesized is that it can reduce loads on the downwind turbines, which can be a significant benefit. But yeah, I think there are opportunities here to build in more sophisticated, more comprehensive, considerations into the optimizations that are done. So if there are these other, trade-offs and criteria that can be modeled at the turbine or at the plant level, I think this method provides an approach for doing that.
Great. So there is another one which I think is quite interesting. That is, did you use flat ground only in the simulations, or does your method also work in mountainous region? This is very important for me as an Italian guy, as flatland in Italy is a premium and it's not very common. And we put wind turbines usually in the hills or even in the mountains because, otherwise it is difficult to find land.
Yeah, excellent question. It's something we've been thinking about a lot, just because terrain is such an important driver of atmospheric conditions and also accessibility for wind farm development. So in the current iteration, we assume simple terrain, but the framework and methods would allow for treatment of those type of things within sort of the graph network structure. And so moving forward, we think that would be a really critical advancement in the technology to be able to capture those terrain effects. Now, it's not trivial to do. There's probably be some simplifications required, but I think that this framework and approach would offer a pathway for starting to more explicitly look at those spatial considerations.
Cool. Thank you very much. One last question very quickly. We already ran out of time, but I think it's very interesting, so I'll ask it anyway. Can you give us some figures about the training time, the computation effort in order to create the simulated data and then to train the model?
Yeah, creating the simulated data was intensive. We used our high performance computer and ran everything in parallel. So using Floris, one of the reasons for using Floris as our full form model is that it's relatively efficient in the world of wind plant modeling. And so we can run cases where we're not imposing this yaw optimization relatively efficiently. Maybe on the order of each run would be maybe 30 seconds or so, depending on the farm. But for doing the optimizations for the farms that have 200 plants, even on a supercomputer, that could be 3 hours. And so it was a very significant. I don't have the sum of the total number of minutes right in front of me, but using the supercomputer, it was intensive. But again, it allows us, once you do that upfront investment, you've got a really robustly trained model, and you can explore a wide variety of scenarios, which is really kind of the benefit of the surrogate approach.